Okay, so I'd like to start by thanking the organizers for inviting me to give this talk about recent work at the Technion. So the work was done in my lab at the Technion. The samples come from Kyoto and from Kyoto. Okay, so really what spurred this work was this plot, which comes from a paper from 2012, where you can see a measurement, the results of a measurement of the penetration depth as a function of doping in one of the pnictides. So this is this material, which I will mention, which I'll explain more about later. And this is a really weird measurement because you can see that there's a very clear peak here at optimal doping, which is kind of counterintuitive because it tells you that, in a sense, at the very doping where superconductivity is the most robust, in this material, it's really the worst because a superconductor, its main attribute is the Meissner effect, main hallmark, and this tells you that at this doping, this material can least expel magnetic field. So this was very curious, and we wanted to follow up on this, especially since, as far as I know, this is the only such measurement. So there are many examples that I can give you. Here's one from a closely related material. So this is this material. Instead of phosphor doping, there's cobalt doping. And you can see here, these black dots are a measurement of the penetration depth as a function of doping. And you can see that, if anything, there is maybe a shallow minimum at optimal doping. So that's kind of more intuitive. What is also missing in this plot is what happens when you get to very low doping. Here it seems like lambda is going to something finite. Here it's increasing. So we wanted to follow up on this, and this is the main topic of the first part of my talk, maybe most of the talk. So I'll tell you a little bit about the pnictides. Max gave a lot of the material that I figured he would give, so I didn't prepare it. So that's very good. And then I'll explain a little bit about how we measure. Then I'll show you the results of the measurements on the penetration depth. I was told once that you should never keep your audience in suspense. The peak is real. So a talk is not an Agatha Christie novel. And then I'll tell you a little bit more about Vortex decoration, which is another tool that we use. So I'm talking about this family of iron-based superconductors. It's the 122 pnictides, and this is their structure. And specifically, we'll be doping by looking at samples where the doping is by replacing arsenide by phosphor. This material is completely generic in its phase diagram, so I'll be showing phase diagrams from a different material. But basically, when you cool your sample, it first undergoes a nematic phase transition from tetragonal to orthorhombic, and then it goes through a spin density wave transition to a spin density wave state, and these states are very closely associated with one another. They always almost always come together. And then if you cool more, you get to the superconducting phase. So here's the superconducting phase, and you can do this. This phase diagram has doping and temperature. The doping axis here, the way you can induce superconductivity from the parent compound is by a variety of means. You can either dope by electrons, so this is this cobalt-doped compound. You can dope by holes. You can use pressure, or you can do isovalent doping, which is what we do. So here's a generalized phase diagram. Here you see Hall-doped compounds. So you see this similar general structure. Here are the electron-doped, and here's this other axis, which is why I like this plot. This is relevant for our samples. This is the isovalent axis. So you induce chemical pressure. You just exchange these two isovalent atoms with one another, so you don't induce any charge. So this is fully compensated. But the phase diagram is very typical in general, except that it has some weird features. Actually, one thing that I should say, people, because of the nature of the doping, these samples are considered to be very, very good samples. There's less disorder. So maybe some of the stuff that people see is because of that. So there are there are several weird effects that happen in the phase diagram above optimal doping. For example, if you look at transport, it has the wrong power in temperature above optimal doping in the normal phase. If you try to measure the mass by a variety of means, and that's not a trivial thing, then you see that the mass increases, seems to, I don't want to say diverge, but it increases where the maximum seems to be near optimal doping. There's other effects that you can see, like there's strong magnetoelastic coupling, which is also weird in this material. And then there's this peak in lambda, which is interesting because it happens inside, below TC. So all of this points to something weird happening around this point. Okay. So the nature of this peak is still debated. People talk about it's under debate. People talk about a quantum critical point existing at near optimal doping, where you are transitioning from the right. If you go in from the right, from a conventional or a superconducting phase, and then on the other side there's a mixed state, superconducting spin density wave state. So maybe there's a quantum phase transition between these two states. But this is getting a peak is not an easy task. And in fact, this is a pretty recent paper where there's an idea that what happens here, what gives rise to this peak, is an emulsion between these two phases. So they're phase separated on a scale that's not known, but it could be down to nanometers, but it could be much bigger. And maybe these materials are less disordered than other pnictides, where if the disorder is greater, then the scale is smaller, and then this could be a reason. But again, this is under debate. This is a plot from this theory paper. Okay. So our goal for this work, our goals are listed here. First of all, measuring the penetration depth is the absolute value of the penetration depth, which is what we're talking about, is a hard experiment. Okay, so if you get a result in one group, it's worthwhile repeating, especially if this result is weird. Okay, so it's worth repeating even if you use the same technique. Now, our technique is is different. It's kind of orthogonal to the other techniques that people use. We work in, well, the most notable thing is that we don't sample over the whole sample. So our measurement is spatially resolved on a scale that's not worse than microns. Okay, so maybe down to 1 lambda. We don't need an area that's more than a few microns wide. So that is worthwhile doing, and then you can maybe get information about heterogeneity and stuff like that. And finally, we can do imaging, and so we can maybe get hints of other phases that exist. Okay. So the samples, here are pictures of all the samples. So we had samples from the Matsuda group in Kyoto across the whole superconducting dome. So pretty low doping to pretty high doping, going through near optimal doping. And we did a set of measurements on each of them. Okay, so next I'll tell you about the probe. So we use a local probe, and that's a spatially resolved probe, and that's really useful because you can move this thing around. So you get a sample. We don't have to do a lot of device fabrication. We can just find a clean area on the sample, bring the tip to the sample, get a measurement of the penetration depth, go to a different point, do this again. That's very, very convenient. We can move away from all kinds of inhomogeneities, cracks, edges. These are all problems in measurements where you have to measure the whole sample. So that's really nice. So that's one thing that we do. We can also look at samples in finite magnetic field when there are vortices, and then we can both see where these vortices are and then get information about defects in the sample, and we can also drag them around. And vortices are it's kind of neat because a vortex in a field, it's going to run from one side of the sample to the other side of the sample, and then you pull on the top. Or, first of all, if it's sitting somewhere, it means there's something in the bulk. It's not a surface. You're not necessarily seeing a surface effect. And then if you drag this thing, then you can, I don't know, you can call it vortex microscopy if you really wanted to. So we play with that a little bit. Okay. So this is another reminder of the length scales involved. So this is really a slide about vortices, but the conclusions are general. So there are two length scales. This is the penetration depth and the coherence length. And in the Pnictides, these are strongly type 2 materials, like the cuprates. Lambda is hundreds of nanometers. The coherence length, which is the size of the vortex core size, approximately, is just a few nanometers. We're doing imaging that ultimately comes from magnetic field. So the scale for magnetic fields at the surface of the sample is given by the penetration depth. And that's our imaging resolution, ultimate imaging resolution for superconducting, for superconductors. That doesn't mean that we can't see things that happen on a really small scale, because if you see something moving, then and you have a good signal to noise, you can be sensitive to things that are even on the scale of the coherence length. And the coherence length is important because that's what's going to determine how, for example, when we do vortex imaging, where vortices sit, the way they get, the reason they sit somewhere is that the core likes to sit somewhere. So that's the scale. Okay, so the tool that we use to get to this sub-micron scale, right? So sub-micron, this lambda is a few hundreds of nanometers, is magnetic force microscopy, and it's a very simple technique. It's closely related to atomic force microscopy. We have a sharp magnetic tip. We bring it to a sample and interacts with the sample, and so a force acts on this sharp tip, and then because of this force, the cantilever that holds the tip is going to bend. Okay, and then you can measure how this cantilever bends, and this is our signal. This is the equation of motion. I'm not going to go through this, but in the end, what we do is we have this cantilever. It has a resonant frequency. If it were in free space, it would be the square root of k over m. But then this resonant frequency shifts by an amount that's proportional to the local gradient of the force. So that's what we measure. And there are various reasons for doing this, for measuring this, and not just how much the cantilever bends directly. Okay, so the first thing that you can do is just find a clean spot and bring your tip towards the sample and measure the resulting signal. So in a superconductor, you get something like this. We call this a touchdown curve. And this signal, if you think about it, means that you have a repulsion, stronger and stronger repulsion of your magnetic tip as you get closer to the sample. This is the result of the Meissner effect, because your tip is magnetic and it's being repelled from the sample. So this tells us that this is a superconductor. Okay, so so now I'll tell you how we use this to measure the penetration depth, and also how we measure the penetration depth itself. So so you can think of this repulsion between the tip and the sample as interaction between a tip and an image tip. Okay, really like the method of images. And then you can derive, we know the London equations, we know the Maximal equations. You can get this, this is actually not that disgusting, but you can get this formula for the repulsion of your tip from your sample, and you can see that the penetration depth appears in it. And if you have a good model for your tip, then you can use this. You can use this to extract the penetration depth. Okay. So this is what we do, and this penetration depth, as you increase in the temperature, it's going to become bigger and bigger. So the signal is going to get flatter and flatter. And actually, this allows us to measure also TC locally. Okay. So here you see a sequence of these images. Touchdown curves, and you see low temperature and increasingly high temperature, and you see that this curve becomes flatter and flatter because the penetration depth is becoming bigger and bigger, and at some point we see a flat signal. This is flat band. This is what you would measure if you would measure a normal metal. And so we can get an estimate from this of TC itself. Okay.
What is the different asymptotic value of that?
Oh, it just offset for. It's supposed to be asymptotic to the same thing. That's one of the difficulties in temperature-dependent measurements is that this offset sometimes shifts. Okay, so we know TC locally, and we can fit these curves to a model, and which I can detail to you later if you want, to get an estimate for the penetration depth itself. So here are SEM images of our tip, which is what we based the model on, and you see that we get very good fits, and there's some tricky things about this fit. So before you use it, talk to me. But from this, for example, in this particular sample, an overdoped sample at this temperature, lambda, the absolute value of lambda is 170 nanometers, and it's really cool that you can measure the absolute value of the penetration depth because it's really hard. It's a hard quantity to get. Okay.
What kind of error?
I would say like maybe 10 or 20 nanometers either way.
Is this best way to model it?
It's basically related to the model. We're trying to get rid of the model. I don't like using a model, but we're trying to get rid of the model, but we're not there yet. So there's issues with this. I have a whole sequence of slides about problems with the fit because you can get a good fit and get the wrong result. So there are tricks that you have to do. But then you play with parameters. We also have uncertainties in parameters. So we're not actually fitting a lot of parameters here. There's things that we set from these images. Okay? So for example, we set this height. Don't play with it too much, but then you can play with it a little bit. The problem is also that the tip, okay, you can see here, this is SEM. I can't see where magnetism is. So there are domains. This is going to affect things too. So there's uncertainty. So it boils down to being, a couple of dozens of nanometers. They're better, if you're looking for differences in lambda, they're better techniques. But it's really hard to get the absolute value. So we did this for this whole sequence of samples. And you can see in this plot, you can see this axis shows you the penetration depth itself, and you see that it has a bump near optimal doping. And we know that this is optimal doping because we also measured TC at exactly the same point where we measure lambda. Okay, so the way we do this is we find a clean spot, we do a touchdown at low temperature, get lambda, and then increase the temperature until we lose the signal, and then we know TC there. Okay, so if the sample is not good, we don't care. It's actually better for us because we go somewhere else so we get a different doping. Okay? So, but you can see that the measurements are so these samples, I'm not showing you very underdoped samples because they're not so homogeneous. These samples are really uniform. You see that you get the same values everywhere. And you see that our results are very reminiscent. They basically corroborate this earlier result, especially if we square. So this is lambda square, so we square 2 and we get a nicer peak. Okay. Another thing that you can do, since we measure lambda and TC at the same point, is plot what's called a Yomura plot. So here's our Yomura plot. This axis gives you 1 over the penetration depth squared. So this tells you something about the superfluid density. And this is TC. And this is all of our samples. You see that they sit on one curve that doesn't care what side of the transition you are. This is very different from the earlier measurement where there were 2 branches. And this could be insignificant, but it could be significant because, it means, for example, that if there's some ultimate TC that you can get to, then it's the same for both underdoped and overdoped. You can see that the power is the same. I can't tell you what the power is because we don't have enough points. Okay? So this is all the samples except for the really underdoped samples. And the thing is that the really underdoped samples turned out to be less homogeneous, And so if we measure at different points, we get slightly different values. So if we add those points to the plot, you can see that TC has a spread, and you can see that the penetration depth has a pretty big spread. And anyway, the values are really big. Okay? So this overall behavior is more reminiscent of other measurements in other pnictides where lambda shoots up as you get to the edge of the dome, and that kind of makes sense because there is a competing phase there, and it's taking charge carriers away from the condensate, and so the penetration depth it diverges or goes up because of this relationship. If you add these points to the Yomura plot, you see that they are really different from the more highly doped samples. Okay? So here you can see, so what's significant about these points is that, as I told you, you see these are measurements from 2 different samples, and there's more than 3 measurements. There's 4 here, so you can see that they look kind of like this. At first you think this is an error, but then you realize, but I measured TC and lambda at the same point, so I might as well plot them one is a function of the other because maybe I don't know the doping. And so this is what's nice about this plot, because you see that they kind of cluster around here, and you see that maybe there's a relationship that TC increases when lambda AB decreases. The way this happens is really interesting, and we don't have enough samples to say anything about it, but it would be interesting to look at what happens out here. Okay, so the next thing that I'm going to show you is what we do with vortices. So this is newer stuff, never before seen in a talk by me, shown in a talk. It has been seen, but not shown. So first of all, I'd like to start by reminding you, we're going to be looking at vortices. So if you solve the London equations and there's a vortex, what you end up with expression that you end up for the magnetic field, for the magnetic field is this expression, and if you look at it closely, this is the magnetic field for a monopole. Okay, so you're going to see like the magnetic field for a point magnetic charge. Okay, this is what the magnetic field looks like when you're scanning over a superconductor, and this monopole sits at some position in the plane, but then it sits 1 lambda beneath the surface. Okay, just to so everybody's not surprised by what we see. And so we field cool, we trap some vortices, and then we see where they sit. So here's an example of a scan. This is the way we get these scans, we move the tip back and forth in one direction, and then we slowly increment it in the other direction, and this is the signal. The color plot here gives you the frequency shift, which is proportional to the local gradient, and you can see that these round objects, and these are vortices. And if you were to fit to the formula I just showed you with the model for the tip, it would be reasonable. Okay, so we looked at all of the samples, and it turns out that for most of them, the ones that are not underdoped, the vortex arrangement, when you field cool, is kind of organized. You don't see signs of terrible disorder. This is actually quite ordered. To be able to see something that looks like an abricosov lattice at 9 Gauss tells you that the sample is really good. You can see here that the vortex positions are not completely random. There's probably more disorder here, but it's still pretty ordered. And you'll see what I mean. No, these are the same exact samples. And you can see, so for anything that was not, for all dopings, so optimal doping is 30%, so 28 and above, we see this ordered lattice. If you go to very underdoped samples, these are the samples that were very scattered, then you really don't see vortices very well. So this has 2 reasons. One, lambda is big, so we lose resolution. The other is that vortices are pinned very, very weakly. So when a vortex sits somewhere, it means that something is holding it there. It's stuck in a potential well. Here you can see that we can move vortices. So every time you see the signal see these lines, these jumps? This means that the vortex was stuck somewhere, and the tip, which exerts a force on it, can drag it. And this means that the pinning is very weak, and this is really weird because the force that we can apply depends on the penetration depth. If the penetration depth is weaker, we can apply a smaller force. So there's very weak pinning, and one could speculate about the origin. So it tells me, the first thing that when you see something like this that comes to mind is that, okay, there's a lot of disorder. Because there's a lot of disorder because because to get a vortex pinned somewhere, it means that it has to be energetically advantageous for it to sit there and not somewhere else. So, but if the sample is bad everywhere, then it's going to be weakly pinned, and we know that these samples are not very homogeneous. And this could come from just mundane defects in the material, but it could also tell us something. Maybe it's trying to tell us something about something that's more profound. Maybe it's telling us that maybe this disorder is intrinsic, so it comes from electron interactions. It doesn't have to come from the crystal. We don't know. I mean, this is something we don't know. This is a speculation slide. Also, it could be that because there is a competing phase and we're losing charge carriers, then we're losing pinning because the core is getting bigger. So that could be consistent with having a competing phase taking away charges from the superconducting phase. Okay. So for the rest of the talk, I'll talk about mildly underdoped samples in which we see lines of vortices. Okay. So this is one of these samples, and you can clearly see lines. And if you try to align them with respect to the crystal axes, then you find out that they're about 45 degrees to the crystal axes, which we know from a separate measurement of the same sample. And this tells us that these lines of vortices are parallel to twin boundaries. So as we heard in the previous talk, there's a nematic phase transition at this doping in this material, and that means that you start from a high temperature tetragonal phase, and then you have to break symmetry and go to an orthorhombic phase, but then this transition doesn't happen everywhere at the same time and with the same orientation. You have to choose a direction, so you get twin boundaries. So these are boundaries where on one side the crystal is perfect in one way, and it's perfect, and on the other side it's perfect as well, but the crystal axes are inverted. Okay? So this tells us that there are twin boundaries here. The vortices, and initially we thought that the vortices are pinned to these twin boundaries. This is something that we're used to from other materials. So here's an example from my lab where you see vortices on a twin boundary in YBCO, a cuprate. There are no vortices. I mean, all of the vortices, they're very strongly pinned on this line. Okay, we use this in this work. We know very well the vortices pin on this plane, which is perpendicular to the surface of the sample. Also, in the iron-based superconductors, there are measurements. So this is a measurement of ferrum selenium, and by STM, and you can see, first of all, with imaging, you can see that vortices sit on. So in this work, they say that these are twin boundaries, and the vortices clearly sit on whatever these lines are. I mean, it's pretty well checked because in STM you can see the atoms, so you know the crystal axes. These are twin boundaries. I don't know why they bend, but they do. And vortices clearly sit on the twin boundaries, and in STM you can actually measure the gap, and you see that the gap is suppressed on this twin boundary. So it kind of makes sense. The gap is suppressed. You have to pay less energy to put a vortex on a twin boundary, so it's trapped there. Okay, so after seeing these lines, we started playing with this sample, and here you see an example at a rather high magnetic field, and you can see these lines. And the trick is actually to go to lower field, and you can still see lines, but then if you go to even lower field, then you see something weird. Yeah, it's always a 2 micron. It's approximately, yeah. I didn't align. We're trying, this is new, so we're aligning. In a month, I'll show you how they align to each other. But the point is that there are stripes here. So if you look at this plot, there's a modulation in the signal. And this is a Meissner signal. So the repulsion of the tip from the sample is stronger here than it is here. And the vortices actually sit between these lines. Okay? If you go to even lower field, you see that these lines survive even when there are no vortices around. Okay? So there's a modulation of the superfluid density, maybe, as you go across the sample. This survives even when you flip the field. So, and I don't want you to think that these things are periodic, which is another reason I'm showing you this plot. So there's nothing periodic in the positions of these stripes. We think these stripes are twin boundaries, and they just happen to be where they happen to be. And you can see that these same stripes appear at low negative field and higher positive field. You can see that their width is on the scale of lambda. Yes?
So they're always along the twin boundaries, right? So this is just
So we don't know that they're twin boundaries. We don't know. What we know is that they're parallel to twin boundaries. I think that they're twin boundaries. We do see sometimes domains with 90 degrees orientation, but not many, but yeah.
Do they go only one way, right?
Yes, for the most part, yes. Well, sometimes we see perpendicular, which makes sense. Okay, and so these stripes, I forgot to highlight this. They're about, the scale for their width is the penetration depth. Okay, that's an important hint. Okay, so, and they also, another thing is that they disappear as you increase the temperature. So we lose them below TC, but that's because of our signal to noise.
They go along crystallographic direction.
45 degrees.
So it is.
Yes. So TC here is 22 Kelvin, and we lose them here. You see how they disappear. So
The longest strike, you have stronger superconductivity or weaker? What do you say?
so yes. So the white stripes correspond to so when you say strong and weak, do you mean TC or do you mean the penetration depth? So it's two different things. They're not, the relationship between them is not trivial. There was one more test that we did with these guys that I want to tell you about it, and that is we can use magnetic force microscopy to manipulate vortices. So one of the downsides of magnetic force microscopy is that you're exerting a force on your sample. So instead of so we use it to our advantage. So we can scan with the tip far away from the surface. We call this a surveillance scan. And then because we exert a very weak force and then a weaker force and then we are imaging, or we can bring the tip closer to the sample. If it's close enough, we can move things. So we tried to move vortices across these boundaries. So here's a surveillance scan. You see a vortex. You see one of these stripes. Maybe. Do you see it? I think you see it. And then we tried to bring the tip. We brought the tip much closer, and you can see that this is what a vortex looks like when you're moving it. And it would not go closer to the stripe. We tried this in all kinds of configurations. Here we tried to push it towards the stripe. We failed. Here are more attempts. We just can't cross them. Okay? So these things repel vortices. Here's another. This is a higher temperature. It's a bit harder to measure. There's two stripes here. You can see the vortices they can't cross. Okay, so these are barriers for vortices. And okay, so this is something that has been seen before. It's been seen in this electron-doped Pnictide. So this is a measurement done in a set of measurements done in the Molar lab, where using squid you can see stripes. They also did some vortex manipulation and vortex imaging. The thing is that the scale here is very, very different from our scale. So if you put our images on the scale, then these images are limited by the size of the resolution limited. Our images are not. So the scale for these stripes is lambda. It's well within our resolution. The thing is that I don't think that these stripes in the superfluid density have been seen other than in this measurement in the molar lab. Actually, at the time when this started, I was there as a postdoc, and we looked for these stripes in this material using MFM, and we couldn't find them. And so there was a question mark, small question mark about, you know, why do they see it with squid and don't see it with MFM? And indeed, you can see it with MFM. Maybe we just landed in the wrong part of the sample at the time. Okay, so you can actually model. There's a phenomenological model for trying to figure out what is your signal going to be if you're looking at a superconductor with a non-uniform penetration depth, and you can see that we can actually fit our signal quite well. I would consider this a plausible, like this model that was developed actually for the molar lab measurements works also for us, but for me it just means that the model is feasible. I'm not sure that I wouldn't consider this a fit yet. We don't know where these stripes, like why would the superfluid density be enhanced on these twin boundaries? Something that I don't think is known. People discuss two-dimensional twin boundary superconductivity. It's been discussed a long time ago. Mostly people talk about enhanced TC, not enhanced. I haven't seen almost anything about enhanced superfluid density except for this work where they did simulations that were supposed to apply to the Pnictides, but I don't understand it yet. There is something interesting. So the material that I showed you before, this ferrum selenium, is a cousin of these materials. That material in that material, twin boundaries are traps for vortices. And that material is different from other Pnictides in that in that material, there is no magnetic phase, as far as I know. So maybe these stripes have something to do with the magnetic phase. Maybe people think that that the magnetic phase provides the glue for superconductivity. So maybe on this twin boundary, fluctuations are easier, and so maybe that the glue is stronger. I don't know. I mean, this is speculation. We don't understand it yet. It could be that it's an uninteresting problem. Maybe it's just details of parameters in some Hamiltonian. My time is pretty much up. This is my summary slide. I'll leave it up for you, and we can discuss further.